this video we will introduce another concept called the compressibility factor. Recall that ideal gases are those gases with temperatures way higher than the critical temperature or pressure that is way lower than the critical pressure. So if the pressure is very low, then that means if you consider this figure a gas inside a piston cylinder device, so at very low pressure, that means that the distances between molecules are insignificant, or they're very far from each other, so somehow the interactions are not significant. But what will happen if we increase the pressure, as in this case, as in this figure? So if the pressure is increased, then that means that the distances between the molecules become significant, and therefore the interactions becomes significant, and we have to take into account the effect of those interactions. So therefore, if we want to use the equation PV is equal to RT, then having this conditions or increased pressure, that means that somehow there's going to be deviations from these ideal conditions, and that is why we are going to introduce this compressibility factor, and we use the symbol Z. Now, when using the compressibility factor, we actually we are going to obtain it or retrieve that using a chart, and there is actually a unique compressibility chart. So there is a unique compressibility chart for each type of gas. So say for air, there must be some compressibility chart, or for nitrogen, or for oxygen. But says here, however, a generalized chart, one that is applicable to all gases, is practical. So if we can have only one chart for all gases, then that would be great. Okay, and such chart was actually developed by Nelson and Aubert, and it works for all gases. Okay, so here's an example. So this is the chart, Nelson-Aubert generalized compressibility chart. So this chart, along this horizontal axis, it says here reduced pressure, and on the vertical axis, that's the compressibility factors. And we have lines here, the blue lines and the dashed lines. The blue line stands for the temperature. TR is equal to 1.0. So 1.0, 1.5 up to 5.0, and TR stands for reduced temperature. The green dashed lines, that's the reduced volume VR. Okay, so here's the equation for how to find the reduced pressure or reduced temperature or reduced volume, pseudo reduced volume. So there is an equation for that. So for reduced pressure, it says P all over the critical pressure, and for temperature, it says T all over the critical temperature. So whenever you have these two properties, then you can actually obtain the compressibility factor. So say you have this pressure at 0.5, and say that when you computed this reduced temperature, it's right here. So meaning from 0.5, you have to project a line up to the corresponding reduced temperature, and then from that interaction, then project a line to the left towards this compressibility factor axis. Then you obtain now your compressibility factor. So Z is equal to, say, 0.8, 0.8, or if it's somewhere in between, then you just have to read the lines. Okay, so here is chart number 1, and that means there is another chart, chart number 2. So here's the chart number 2 as shown here, chart number 2. So the difference is, if you notice this pseudo, or the range of the of the reduced pressure, This is 0 to 1.0. And when using chart number 2, the 0, and here's 1.0, and you have all the way here to 7.0. So that means that the chart number 1 is just somewhere right here. So it's like a zoom in view. So you see here 1.0, and the compressibility factors from 0.3 to 1.0. So here, so that means it's like it's somewhere here. Okay, so it's like zooming in into this chart. Okay, so again, here is the equation for the reduced pressure. So P all over critical pressure. This one is, the value of the critical pressure and temperature. They are available in tabulated values. And then the value of P and T, they are the ones that's given. So you can solve that, then you can find the reduced pressure and reduced temperature. Okay, so here's the properties of some ideal gases. So substances, the formula, the gas constants, a specific gas constant, and then the critical temperature and the critical pressure. Now, if in case we have substances other than the ones listed here, then that means you might want to look for another tables. Okay, so another table, it's still the same. Somehow the same, that it's about the properties of some ideal gases. And here we have extended values like for refrigerants, so R134A, R11, R12, R21. Okay, so here we have here's the substance, and here's the specific gas constants and the critical point properties, the temperature and the pressure. Okay, so I think that's all for this topic. So now let's move on to the sample problem. So for our sample problem 4.3, this problem is taken from one of our reference texts. It says here that 0.016773 cubic meter tank contains 1 kilogram of refrigerant 134A at 110 degrees C. Determine the pressure of the refrigerant using A, the ideal gas equation, and B, using the generalized compressibility chart, and let us see the refrigerant tables. As I've said before, that the properties can be retrieved in various ways. So one way is through the use of tables, property tables, or charts. We can also use charts and also equations. So this sample problem just represented that we can actually find it in various ways. The pressure property, we can find it in various ways. So whenever they are available, or let's say if we can consider it as an ideal gas, then we can use the ideal gas equation, or we can use the compressibility chart. And if there's tables available, refrigerant tables available, then we can also use that. We can retrieve the properties. Okay, so first step, as usual, so solution. So for number 1, illustrate the problem. Illustrate the problem. We have a tank with a defined volume. So let's say we'll use cylindrical shape, and this is R134A. And then the volume is 0.016773 cubic meter, and then M is 1 kilogram. The temperature is 110 degrees C. Okay, so since this is a refrigerant, then, and since we'll be using ideal gas equation, then that means we have to find the specific gas constant. And so R, or from table um, of ideal gases, ideal gas properties, then R is equal to, so what is R? So here the R134A, it's not actually available in this table, so that's why we have to include this. So first column stands for that's for the substance. So here we have R12, R21, and here is our R134A. So R134A, and this column is the specific gas constant. So R134A is 0.01 0.08149. So 8149, that is kilojoules per kilogram K. Kilojoules per kilogram K. Okay, so now we can apply the ideal gas equation. Okay, applying now the ideal gas equation. Ideal gas equation to solve for the pressure. So recall PV is equal to total volume. PV is equal to MRT. So P is equal to the mass. This is 1 kilogram. 1 kilogram times the R value, 0.08149, and then the value of T, this should be in Kelvin, so 110 plus 273. So 110 plus 273, that's for Kelvin, and divided by the volume. Volume is 0.16773. 0.016773 cubic meters. Okay, so now let's compute. So 1 times 0.082149 times 110 plus 273 divided by 0.016773. This is 1860.7. 60.7. This would be in this is kilojoules, then kPa. Okay, so next one is when using the chart, the compressibility chart, stability chart. Okay, find the critical pressure and critical temperature first. Okay, so critical pressure or the reduced pressure. Reduced pressure. Find the reduced. So P reduced is equal to P all over the critical. The reduced temperature is equal to the temperature divided by the critical. So for the pressure, we have, what's the pressure? 1860.7. 1860.7. Then the temperature is 110 plus 273. 110 plus 273. 383. Okay, so now let's obtain the values of critical pressure. Okay, so here's the value for critical temperature. We have 374. So 374, and then the pressure is 4 point, so 374.2. So 374.2 and 74.2 and 4.059. This is 4.059. So this is in Kelvin, and this one is in megapascals, but this one is in kPa. So we have to convert one to the other. So 1860 kPa, 1860 kPa. So this one would be 4,000, 4,059. Okay, so let's compute this. $1860.7 divided by 4,059. We have 0.45 or 0.46. 0.46. Then next one is 383 divided by 374.2. This is 1.02. So now let's go to the chart. Okay. So from the chart, so let's draw a chart here. Our reduced pressure is let's say 0.5, and the reduced temperature is 1.0. So 0.5. So here it is, 0.5, and then goes to so 0.5, so starting from this, then it intersects with this TR is equal to 1.0. Then here is 1.8. Then we have 10 divisions here, so that means this is 0.81. So Z is equal to, so from the chart, Z is equal to 0.81. So now applying this so now applying now the reduced what's this? The compressibility factor. Applying now the compressibility factor. So recall again, PV is equal to M RT times Z times the compressibility factor. So it's just the same values here. So therefore the pressure would be 1860 times, so 1860.7 kPa times 0.81. So 1860.7 times 0.81. This is 1507 kPa. And then when using tables, then we go to our property tables. So here in the bookmarks we must go to this superheated. It's actually superheated because the temperature is, so check again, we are above this critical temperature. So our temperature is T8 is 383, while the critical temperature is just 374. So that means we are in superheated. Okay, when using tables, since T is greater than the critical temperature, that means we are in superheated vapor region. So now in these thermodynamic tables, we'll be entering table for superheated R134A. Okay, so here it is, table B.5.2, superheated R134A. And we have to find, since the given what's given to us is the specific volume and the temperature. Recall here the given is specific volume and the temperature 110 and the 0.016773, and the pressure is, that's what we are going to find. So starting here, we have a temperature of a range of temperature at this pressure. So at this pressure, what is the specific volume? Is it 0.016773? So if not, then we need to jump to the next pressure. So volume at 110 here is 0.6, so that's not what we're looking for. So here the volume again is not. So you can actually see here 50 kPa, 100 kPa, 150, 200, and check the volume. And since what we have computed here is the pressure is around 1500 kPa, so that means more or less we are in that pressure range 1500. So let's check here, 1400 at 110, the value is 0.01958, and again our what we're looking for is 0.0167. Okay, so next pressure range, the 1600. So at So here at 1600 kPa, what's the value of 110? So here is 0.01676, and if you check here at this 2000 kPa range, the value is 0.01279. So more or less it's somewhere here, right? So that means if you check here again, so the 110 value is only this. So that means the pressure at this specific volume and temperature would be 1600, right? So therefore pressure is equal to 1600 kPa, right? So you see we have three values for the pressure. If we do a summary, so pressure, okay, so summary. So when using ideal gas equation, our pressure is 1800 something, 800 kPa. Then when introducing or incorporating compressibility factor Z, our pressure is 1500 kPa. And when using tables, our pressure is 1600 kPa. So more or less we are at the same range, but as you can see here, if we're using just the ideal gas without without including the compressibility factor, then our error with respect to these values, table values, then that means we have a greater percentage of error. Okay, so that's all for this sample problem 1. Then next we'll move on to the another sample problem.